In this lecture, I would like to talk about BET theory of multi-layer adsorption. As we learned that Langmuir adsorption isotope, it is actually restricted to the formation of unimolecular, monomolecular layer of the gas molecules on the surface, on the solid surface. But Langmuir adsorptions actually does not actually supports the or explains the formation of multi-layer adsorption. That may actually the possibility for the adsorptions. That is the usual expectations of adsorptions for many examples, many cases. But Langmuir adsorption isotope actually explains the monomolecular layer formation, but it does not actually supports the formation of multi-layer adsorption. But BET theory, it actually supports the multi-layer adsorptions that are taking place on the surface. That is, it actually supports the physical adsorption. This theory is actually proposed in 1938 by three people together, Brunner, Emmett, Teller, and the first letter of these people, the name of these people is, Brunner, Emmett, Teller. The first letter of their names actually uh, 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 is actually BET. And some of the assumptions that they have made um, can be listed as follows. And this BET theory actually assumes that the solid surface possesses the uniform surface, and they have localized site. I mean, that the absorption on the one side will not affect the absorption of at the neighboring site. What I mean here, if you have this is considered, this is a surface area. This is the solid surface. You see one of the sides here. Absorptions at the site will not anyway affect the neighboring sites, neighboring absorption sites. So the another point is that they can form the molecules can form a second, third, and nth layer. This is your solid surface. This is monolayer, and this actually assumes that the formation of multi-layer, that is the second layer and then third layer absorption can also happen. And the surface area for nth layer, you just consider this is the nth layer somewhere here. This is the nth layer. The surface area available to form this nth layer is actually equal to the n minus 1, the that the area covered by the n minus 1 layer. Yes, I'll repeat again. The surface area that is available for the formation of nth layer is equal to the area covered by the n minus 1th layer. Yes, this is another assumptions made by these people. And the most important assumption is that the energy of absorption, that is the heat of absorption. The heat of absorption is in the first layer is considered to be E1. E1 is actually it is a heat of absorption. It is a heat of absorption, or simply you can say it is a energy of absorption for the in the first layer. That is most important. Heat of absorption in the first layer. The meaning is the heat that is evolved in the formation of monolayer, the first layer of absorption, is denoted by this by E1, by E1. And The another term that we usually encounter in this equation is EL. EL is actually energy of absorption. This is energy. This is energy of absorption. This is energy of absorption in the further layer, I mean the second and third layers, or simply you can say the succeeding layers, succeeding layers. EL is actually the energy of absorptions involved in the second, third, and etc. The succeeding layers, EL. And this is actually considered, this is the EL. This energy is considered is same as the energy of liquefaction. The energy of liquefaction of the adsorbate gas molecules. Liquefaction, right? Liquefaction of the gas. Let me again tell you, EL is actually the energy of absorption, of the succeeding layers. It is not for the first layer, the other layers, and that is actually same as the energy of liquefaction of the gaseous adsorbate. Liquefaction is actually the energy involved in the liquefaction. So that is the condensations from the gas to the liquid, that is called, you have gaseous molecules. When this gaseous molecules now is going to be condensed to liquid phase, the energy involved in this phase transition is called liquefactions. You can also call this as condensation process. So EL is actually the energy of liquefactions of the gas. This is considered to be same as the energy that is associated with the succeeding layers. The next, based on these these assumptions, this Brunner, Emmett and Teller, they actually proposed the following equation. That is, P by V total. Let me explain what is V total and P naught and P naught equal to 1 by V mono into C minus C minus 1 divided by V mono C and P divided by P naught. This is actually the BET. This is actually the BET theory, the equation. This is called the BET theory. Okay. This equation actually explains the formation of the physical formation of multilayer. That is more important. This equations explains the formation of multilayer adsorption. And before that, let me explain the terms involved in V total. That is V total is actually the volume absorbed, and the V total is actually volume of gas that is absorbed at the pressure P. At the pressure P, V total is actually the volume of total gas absorbed. Volume of total gas absorbed at the pressure P is called V total. It's simply volume. P naught is called a saturated pressure. P naught is called a saturated pressure. And V mono, that is V mono. It is more important term. That this term V mono is more important term. It is actually volume of absorbed volume. It is actually volume of absorbed gas that's actually required to cover the monolayer, to completely cover the monolayer. If you have just consider, you have a surface over here. this V mono is actually the volume of gas that is actually required to cover the whole surface area, the whole surface area, that is the volume required to cover the mono layer is called V mono, right? Then C is called simply a constant. C is actually simply a constant. This is this is uh, this is C is given by e power E1 minus EL and divided by RT. This is a constant C. um, okay, then now you see here, C is a constant. C is a constant, and uh, okay, what I'm going to do is I'm going to plot this equation. I'm going to plot this equation. This is actually plotted in the y-axis, and this p by p naught is plotted in the x-axis, in the x-axis. That is, I'm going to plot. I'm actually going to plot uh, um, uh, p by v total, p naught minus p. This is in the y-axis, and the x-axis p by p naught is plotted. So you perform a adsorption, and you find out adsorption. You perform an adsorption, and you plot pressure pressure divided by V total. The volume, total volume at this pressure, total volume absorbed, total volume of the gas absorbed at the pressure P into saturated pressure P naught minus P naught. It is a saturated pressure, right? And minus the pressure P. If you plot this is actually the equilibrium pressure. This P is actually the equilibrium pressure, right? If you plot this, and they have done this experiment, that they have actually plotted for the absorption of nitrogen on silica. They actually plotted this for absorption of nitrogen on silica gel at temperature minus 183 degrees Celsius. So at this temperature, they performed they performed an experiment where nitrogen is actually absorbed on silica gel. For this, they have got the straight line. They have got the straight line. This actually proves that this equation is this equation is, this BET, since you get straight line, therefore you conclude that this equation is valid. This BET equation is actually valid because you get straight line. For forming an adsorption experiment, and plotting these in the y-axis, and this p by p naught in the x-axis. If you plot, you have got the straight line. Therefore, straight line with the slope equal to c minus 1 divided by v mono, volume of mono gas absorbed at the mono layer, into C. And the intercept is actually, see here, this is y-axis, y equal to, this is m slope, this is x-axis, and C intercept. So therefore this is y-axis, this is x-axis, this is slope, and this is intercept. So intercept will be equal to, you see, intercept equal to 1 divided by V mono into C. This is intercept. So the very useful now, this BET theory is very useful to find out the surface area of the adsorbent. Surface area of the adsorbent. Let me explain that, and also let me explain how this BET actually explains the type 2 and type 3, type 4 and type 5 adsorption isotope. First, let me explain. The this is actually the adsorption isotope, type 2 adsorption isotope. This is type 2 adsorption isotope. That is the pressure versus the amount of adsorbed material in the y-axis. If you plot this, is you will get a curve like this. You will get a curve like this. Somewhere here. Let me explain it a little later. B, the point is called B. This is type 2. This is type 2. This is type 2 adsorption isotope. When this isotope actually forms when E1 is actually heat of adsorption in the formation of a monolayer. Heat of adsorption for the formation of monolayer is called E1. That is actually greater than the EL is actually the heat of liquefaction, or the heat of the other the heat evolved in the other layer formation, if this is the condition, you see if this is the condition, what you can understand is that E1, if it is greater, then a lot of heat energy is released when the monolayer is formed. The more heat energy is actually released when the monolayer is formed than the second and the other layers formation. So therefore it actually encourages the formation of monolayer, because in the monolayer only, you see the heat evolved is larger than the heat evolved in the second or the other layer formation. So therefore this when this is the case, when E1 is greater than the EL, then this supports the formation of this type of curve, because you see here, when the pressure is increased, you see here gradually the adsorbed amount actually increases, and up to this point, this amount of adsorbed gases will increase up to this point, and after that, you see the curve is flattened. It is not actually increasing. It has reached the limited value, and followed by further increasing the pressure, you see the amount of adsorbed material actually increases further. This shows me that this adsorption isotope involves the formation of multilayer adsorption. Multilayer of adsorbent is actually adsorbed on the material. So therefore, this is how this BET is helpful in explaining the type 2 curves. And also, you see in type 3 curves looks like this. Type 3 curve is actually the pressure and the Y. If you plot, you see this is the curve that is obtained for the type 3 curve, pressure versus this is type 3. You see here, when E1 is less than the EL. What do you mean by that? And the formation, the heat of adsorption of the first layer is less than the heat of adsorptions for the second and the other layers. So what do you mean by that? That this is let me explain like this. You just consider this is a surface. Before completing the formation of monolayer, they start, you see here, this monolayer is not completed. The formation of monolayer is not completed. Before completion of this monolayer, the second and the other layer started to form, because the heat of absorption is greater than the heat of adsorptions for the first layer, for the monolayer. Therefore it actually involves before completing the monolayer, completely filling up the monolayer, the second and the other layer started to form. This is actually explains the multi-layer formation. This curve actually explains the multi-layer formation. So this is how you see BET is helpful explaining the other types of curves. The curves involved in the second and the third type of adsorptions isotherm. The most importantly, the fourth and the fifth curve is also explained. The third and fifth absorption isotherm is also explained by the same way, but where in the third and the fifth absorption isotherm, they looks like this. The absorption isotherm for the third curve, for the fourth type looks like this. So the fourth type, you see here, when you increase the pressure slightly, you see the amount of adsorbed material actually increases, and then it started, it decreases slightly, and then again started increasing. This actually then reaches this actually this is amount of adsorbed material, this is pressure. You see here, this is also involves a multi-layer formation, but you can compare this with the second type. You see here, this is the type 4 adsorption isotherm. Type 4 adsorption isotherm. You see, this is type 2 adsorption isotherm. This is actually involves multi-step. Up to this first layer is completed, and then second layer started to forming. But here also you see, this is first step is completed and the second step started following. Then how this type 2 and type 4 differs? To explain this, they actually, you see here, when you increase the slight increase in the pressure, you see the adsorbed material, amount of adsorbed material actually increases more. You see here, the slope here is less, here the slope is very high. That is, the increase of adsorptions by increasing the very slight pressure increases the more amount of adsorbate actually adsorbed. So this is actually this observation is actually explained by saying that the adsorbed material is a porous material, and also it has some capillary. You see, this forms a monolayer, and this after monolayer formation, you see this this gaseous molecule is further go inside into the capillary. Somehow the capillary and pores also occupied. So the slight increase in the pressure, you see more number of gas molecules will be absorbed. Not only on the surface, they also go into the capillary, or they go into the pores for the absorption. So that is why you see the slight increase in the pressure, you see more number of adsorbate is actually absorbed. But you can compare this with second type. This is not actually involves the absorption in the pores or capillaries, but here this actually involves the absorption to takes place in the capillaries and the pores. And this type of adsorption, this is fourth type of adsorptions, will favor when E1 is greater than EL. And then the fifth type of adsorption isotherm. You see here, the pressure versus adsorbed material is plotted. You see here, the fifth type of adsorption isotherm looks like this. This actually happens when EL is greater than E1. When then the heat of adsorption is greater than the heat of adsorption for the second and the other layers is greater than the first heat of adsorptions for the monolayer formation. So when this happens, when this is observed, this actually this type of observation actually allows to have the adsorption isotherm like this. This is also explains the multi-step formation. Multi-step uh, adsorption, adsorption to take multi-step adsorption. This actually favors the multi-step adsorption. So this is how BET theory gives explanations for the other adsorption isotherms, formation of multi-layers, multi-layer adsorptions. Then I would like to explain the surface area calculation. Then I would like to explain the surface area calculations. I will do this in another video.